In this video, we're going to explore the intermolecular forces. Besides the ionic and covalent bonds that we've been discussing so far, which hold atoms together within molecules, there are also intermolecular forces. These are the forces of attraction between molecules, and they tend to be relatively weak compared to the intramolecular bonds. So these are generally forces that govern the physical properties of compounds, and so things like melting points and boiling points. So we will also discuss these forces in terms of whether or not a compound is soluble in a particular solvent making a solution, and also they have effects on biochemistry, especially in terms of how proteins acquire their shapes. As a reminder, there are generally three phases of matter. In the gas phase, the gas molecules are not touching one another, but they're in constant motion so that they are moving around within the container. There's lots of empty space, and we generally assume that the intermolecular forces between the various molecules in the gas phase are relatively weak. In the liquid phase, the interactions are such that the molecules are touching one another, but they are free to flow around and move. And so in this case, the attractive forces between molecules is more substantial than in the gas phase. And finally, we have the solid state where there is a regular repeating pattern. So this is the crystalline form of a solid. And here the intermolecular forces are quite strong, and or the strongest in terms of the phases of matter. And so as a result, the atoms are not readily able to move around one another. They're locked into position. And so the solid has a fixed shape and volume, and this is a consequence of these intermolecular forces of attraction. The first of the intermolecular forces that we should discuss are a result of the forming of dipole moments. If you remember that when a molecule forms a bond, if there is an unequal sharing of electrons between two atoms due to differences in electronegativity, the pair of electrons that forms the covalent bond is drawn closer to one of the atoms and away from the less electronegative atom, as we see here in the case of HF. This produces some ionic character, so that in this case, the hydrogen atom is has a partial positive charge, and the fluorine atom has a partial negative charge. This results in the so-called dipole, and as a result, this molecule is referred to as being polar. So this is a vector quantity that has both a magnitude, which tells us about the direction, and the size of the dipole moment. To represent a dipole moment for a simple molecule, all we have to do is to use a vector arrow to indicate the direction in which the negative charge of the polar covalent bond and how that is with respect to the molecular structure. In the case of a molecule having only two atoms, as in HF, this is relatively simple because this vector is pointed right along the bond. The tail of the arrow is given the plus sign for the positive end of the molecule, and the head of the arrow is the negative end of the dipole. The length of this arrow is proportional to the magnitude of the dipole moment. In the case of molecules that have more than one atom, or more than two atoms, then we have to take into account not only whether or not we have polar covalent bonds, but also whether or not the shape of the molecule results in a dipole. So, in the case of something like carbon dioxide, the carbon-oxygen bond is a polar covalent bond, and there are two of them, such that the dipole within each of these bonds is pointed towards the oxygen atom. And the crucial thing herein is that these two vectors in carbon dioxide are pointed in opposite direction and have equal magnitude. That means that there is a canceling of the net vector representing the dipole, and as a result, the molecular structure has no net dipole. As If we look at a molecule whose shape is not linear, as in the case of water, the OH bonds have dipoles. They are polar covalent bonds, and they have vectors in which the oxygen is the more electronegative atom. And of course, there are two of these because of there being two OH bonds. The magnitude of both of these are the same. However, you'll notice that the shape of water is a bent molecule, and therefore what we need to do is to take and break the vector associated with the bond dipole into its components in both the vertical and horizontal direction, as you see here. You'll notice that the two horizontal vectors are pointing directly at each other, and therefore those two components cancel one another. However, the vertical components are both pointed in the same direction, and therefore those two vectors will add to one another, and the resulting net dipole moment is a vector that bisects the HOH bond, and the negative end of the molecule is the oxygen atom, and the positive end of the molecule is right in between the two hydrogen atoms on the lower end of the molecule. The lone pairs themselves are a complicating factor, and they contribute to the dipole moment as well, but the discussion of their contributions is well beyond the scope of our course. So, the crucial thing here is that the overall dipole moment for water is not zero, but is a substantial value of 1.94 dBs, and it is in the direction of the oxygen atom. So the oxygen atom has the slightly negative partial charge, and the bottom of the molecule, as seen here, is the end that is an equivalent amount of slight positive partial charge. It turns out that there's a whole variety of organic molecules that are very closely related to the structure of water. So, for example, alcohols, which have the so-called functional group of an OH group, and then there is some sort of grouping of carbon and hydrogen atoms coming off of the oxygen. You'll notice that there are two lone pairs on the oxygen along with an OH bond. Both the OH bond and the OC bond in an alcohol are polar covalent bonds, and the bent structures result in dipoles. Likewise, if we had a molecule known as an ether, there's an oxygen atom with on either side of the oxygen are groupings of carbon and hydrogens. In terms of what we refer to as alkyl groups, these two alkyl groups can either be the same number of carbons or hydrogens, or could be different groupings. But the crucial thing here is, again, the structure is bent, and we have polar covalent bonds, so these molecules generally have dipole moments as well. At this point, we want to discuss the so-called intermolecular forces, which are attractive forces between molecules, and how this is affected by the presence of dipoles. The forces of interaction for the intermolecular forces can occur between neutral molecules. They can occur between molecules that are the same, or they could occur between different molecules. And they also are important for the interaction of molecules with ions in solution. The first of the forces, which tend to be quite weak, are known as London forces, or sometimes referred to as London dispersion forces. These are temporary dipoles that exist for very brief moments in time as a result of the movement of electrons in a nonpolar molecule. And so by the electrons being located at for some brief period of time, all grouped together on one side of the molecule, this results in a temporary dipole, and the interactions then are relatively weak. The next important force is the so-called dipole-dipole forces. These are the charge interactions between molecules when molecules have permanent dipoles because of polar covalent bonds and their structures being non-symmetrical. And these two types of forces together are referred to as the van der Waals forces. And they are both relatively weak, but the London forces tend to be weaker than the dipole-dipole forces. In addition to that, there are stronger intermolecular forces known as hydrogen bonds, and we will discuss those in detail soon. And then finally, stronger yet are the interactions between ions and molecules that have dipoles. At this point, we want to discuss dipole-dipole forces in molecules that have dipole moments. And so, as an example of this, we can consider molecules such as HCl, hydrogen chloride, which has a very polar covalent bond. The chlorine end of the molecule is slightly negative, whereas the hydrogen is slightly positive. If we had more than one of these molecules in close proximity to one another, we would then have a interaction so that the molecules would line up the positive and negative ends so that the opposite charges would attract one another, and this would result then in this weak intermolecular attractive force that we refer to as a dipole-dipole interaction. So in this diagram that you see here, the intramolecular polar covalent bond is very strong, as you see pointed out by the red, whereas the intermolecular attraction is represented by the red dots between the hydrogen and the chlorine of two different molecules. These intermolecular forces can affect how the molecules interact with one another, both in the solid state and in the liquid phase. If there's a regular repeating alignment of the HCl molecules, as you see here in the solid state, then the hydrogen will try to maximize its interactions with other HCl molecules to get a distribution of the positive and negative charge as evenly as possible. This locks the molecules into position so that you have the so-called crystalline solid. If we add some energy to get the solid to become liquid, some of those interactions tend to be broken, and the molecules are allowed to then change their orientation to some extent and begin to move and can potentially slide across one another. And this is oftentimes what is resulting in the liquid phase.